Welcome to the Jack Westin MCAT Podcast with your host, Phil Hawkins.
And Azaii Calderón Muñiz.
Alrighty, folks, welcome back to another episode. We are so stoked to get to continue doing this series. We're working through the AAMC's sample test, and we're going through each of the passages individually, having the opportunity to help you guys think through how the AAMC test writers think and how we think through this. And along the way, understanding and having a better understanding of how to approach passages, how to approach questions, and not let the stress of the MCAT get to you when you're doing so. And so today we're going to continue on the Chem Phys train, which I'm sure you are super stoked about, Phil. And we're going to do the second passage of the exam.
Yeah, I am super amped. I love chemistry and physics, so you know that about me. But this is an interesting circuits passage, and I know circuits passages tend to overwhelm students a lot. And so that's something that, this is having the idea and understanding of how are we going to get tested on test day helps you understand how you should be studying. We should pause for a moment though. And I just realized that I don't think we talked about talking about this today, but the AAMC had some announcemos recently.
Yes.
And so they will be adding a fifth practice exam on top of their a fifth scored practice exam. Obviously they have their unscored exams. This brings the total exams from the AAMC to 6, which is awesome. And this, I believe this practice exam is going to be free, correct?
Yes.
Yeah. I remember reading that, but it seems like part of me is questioning, is it really free? Is that would be so great. It's been years since the AAMC has released another exam. And so this is a really exciting, useful resource. You can bet we're going to be talking about that when it actually launches sometime here shortly. But in the meantime, let's talk about the exam that we actually have in front of us that we're going to be helping break down. So looking at this passage, just overall, just a quick glance, we can see that there's a table, there's a really intimidating looking circuit, there's a graph. This passage has it all. And also, lots of little paragraphs in here. But we're going to go ahead and just kind of jump straight in here. The central nervous system is an example of an electrical system within the human body. Neurons are the basic electrical components of the central nervous system and exist in 3 classes: sensory neurons, motor neurons, and interneurons. I feel like what they're bringing up here is just the nervous system can be looked at like a circuit. This is not news, right? This is not something that I think students should be oh my gosh, this is super testable. I think these first couple of sentences are just kind of setting the background here. This doesn't seem super testable. You should already be kind of familiar with this stuff before you even get to your exam. But it continues on. Each neuron is made of 3 main components: the nerve cell, the axons, the dendrites. The longest axons are approximately 1 meter in length, and the axon outer membrane is surrounded by an extracellular aqueous solution of protein, sodium, potassium, and chloride. A summary of the electrical property of axons is shown in Table 1 and in Figure 1. I think this entire paragraph here is not that useful, with the possible exception of they say it's 1 meter in length. I think that's the we're in the Chem Phys section. Calculations are fair game. But as I'm going through this, they're just giving me a bunch of background information about neurons that shouldn't actually even be news to us. But they do give us this number here. And so all of a sudden they could ask us to do a calculation with that. This is the longest neurons. So note that there's a lot of neurons that are shorter than that. But if they ask what's the maximum time it can take an axon potential to get from, or action potential to get from one end of a neuron to the other, okay, well, what's the longest neuron? And let's figure out how long it takes in that case. That's just something that was I see that and that could be a question, but everything else is just generally neuro. And so we do want to be thinking neuro. We also want to be thinking circuits, because the door has been opened by the AAMC into those sorts of questions. Now I know that's biology and physics, but that's exactly how the MCAT works, right? They like to blend these topics.
Yeah, exactly. I said this last time, but it's the Phys section in the title of biological systems, right? And yeah, this is actually something I think we've mentioned on the podcast before, the connection between the nervous system and, all things electricity, et cetera. And so these are things that as you're studying, let's say that you do this practice test for the first time and you're like, oh, they connected these two ideas. I should have seen this before. Write it down and study them together, because you never know what you're going to get on test day. Wouldn't get the same exact passage, right? But definitely could get something relating the two.
Yeah,
so
this is not I was going to say, this is just not the first time I've seen the AAMC connect these ideas. Like I've seen them do this like a half dozen times. Yeah.
So zooming into table 1, and, we see this on test day, and our natural response can be to kind of freak out a little bit, right? Because we see a bunch of words, different properties, a bunch of numbers. We know this is in Chem Phys, and we're like, oh my gosh, are we going to have to make a million different calculations, right? So in this, we're just getting some properties. We're not getting some major experiment or some groundbreaking information that we need to really sift through. What we're told is a list of properties, right? And the difference between a myelated and a non-myelated neuron. And so we're going to briefly take a look at this on test day. What we can see is that in the properties, we get things like radius, resistance, conductivity, capacitance. None of these things should freak us out, because the AAMC, like you said, Phil, opened the door to questions about these different topics in the very first few sentences. And so what we can do is take a look at the numbers and gauge the difference very briefly. So for example, the radius is the same in both, right? So right off the bat, I'm like, I'm not going to worry too much about this. With looking at the resistance, the conductivity, honestly, looking at those exponents, the exponents when they're different can be so much more helpful than trying to, figure out, okay, exactly by how much is the difference. And so exponents are your friends as a quick gestalt, as a quick once over when you're going through this. And so I want to have an idea of this when I'm moving on to the questions, but I don't need to have these numbers memorized. I shouldn't have spent, a minute, 2 minutes on this table. It's not worth it. And so identifying when it is worth pausing and really dissecting a table versus not is going to be important. And again, in this case, we just got some properties, no experiment, nothing that they really started fleshing out in the paragraph. And so that's my indication that I'm not going to fuss about this before I get to the questions.
Yeah, I think it's really interesting. Like a lot of times students approach all tables the same. This is not an experiment. This is just, we're telling you the properties of some of these axons. Like they're not actually going in and saying like, oh, under this experiment, under these conditions, this is what we got, this condition, this is what we got. And like, in those cases, a lot of times we're trying to figure out like, what does this data tell us? But here they're just measuring stuff and like giving us the information, but they're not actually doing an experiment. They're just providing information. I do like that context of like looking at the overall numbers. Like note that the axon radius and the resistance are both the same. So the MCAT's probably not going to ask about those things. And so I'm going to kind of like just glaze over that. But we can see here like 10 to the minus 4th, 10 to the minus 7th. 10 to the minus 4th is bigger. And so it's about 10 to the 3rd times bigger. So like I would just like really quickly looking through this table, the conductivity is about 1,000 times bigger in the non-myelinated. The capacitance is about 1,000 times bigger in the non-myelinated. The thickness is about 1,000 times bigger in the myelinated one, which makes sense because the myelin is going to be like add thickness to the membrane itself. I'm just looking at the magnitude overall. Yeah.
Perhaps we can zoom in for the folks that are on smaller screens to see these tiny numbers.
That might be tricky, but let's try to make that happen. Yeah. So just kind of like looking at those numbers overall.
Yeah. And this is something really quickly important to note. When the difference with a negative exponent, right, it's flipped compared to a positive exponent. So make sure, in the sense that larger means smaller with a negative exponent. So make sure that you're comfortable with the basics on test day.
Negatives are tricky. I always like phrase it to students like, if you have more money, do you have more money in your bank account when you have negative $4 or negative $7? All of a sudden that makes a lot more sense. I'm like, okay, negative 4 is more money in your bank account. It's still negative, but it's better than the other one. So negative 10 to the negative 4th is bigger than 10 to the negative 7th.
Mm-hmm. Now, looking at this kind of next figure that we're given, This is intimidating for a lot of students because we're like, okay, what are we looking at? We see some resistance, we see a circuit. Do I need to break this down right now? We don't have information to break it down, right? We don't really have anything actionable for this. And so we're told that it's a simplified circuit of an axon. That's all I'm going to worry about. I'm going to see that we have some in series, some in parallel, but that's it because I don't have anything else to go off of. And so when I see that and I start freaking out, just kind of going to register, okay, I can move on. This is a safe opportunity to move on.
I think that there's a really good idea here of like when students look at this, a lot of students are panicking, like, I don't have enough information to tell stuff about this. Like, how do I deal with this? The answer is you don't, right? Like the fact that they didn't give you a lot of information for this actually means that you should be worrying less about it. I mean, there's a lot of things in here, RI, RM, R not. I don't know what those things mean. Like they actually don't clarify that anywhere. This is just a figure that was in that original journal article. And so they've included it here, but there's not enough context for us to actually ever do anything with this. And so I don't think they can ask a question about this. So I'm not going to spend any time on it, which makes our lives a whole lot easier. And so not only, I'm not telling students that you shouldn't be able to deal with circuits, but like they don't give us enough information here to do anything, so they can't ask us a question unless they give us a lot of information in the question itself.
Exactly. Nothing to add to that.
Yeah. So continuing on, we have like scientists can study the electrical property of neurons by inserting probes into them to measure the voltage changes as a response to stimulus. A typical plot of this action potential is shown in figure 2. Now this, all of a sudden, this is actually kind of an experiment. They said like we did some stuff to measure and then this is what we got out of that. So I think this is something I would want to pay a little bit more attention to. We have like the voltage here. We know we go from a negative to a positive voltage. We depolarize. So this is a depolarization. So we go from negative to positive, and then we'll repolarize going back to negative again. But they also give us like we have voltage as the y-axis and time as the x-axis. You want to pay a lot of attention to millivolts, milliseconds. They even go into some extra time here to show you that this is 1 millisecond. Every one of those ticks along the x-axis. So I think that there's a chance they could ask us something about this. They love to ask questions about neurons, and there's some data here that we could actually do something with. I think of all the stuff we've seen, this is probably one of the first ones that I would expect to see some significant questions on.
Absolutely. And another indication that it could be important is this should look familiar. This should not be something brand new, right? You should know what an action potential looks like. You should be able to, have an idea of what that potential difference, right? That voltage is across the neuron's membrane. And so the fact that I should recognize this on test day is another indication that, hey, I could get a question on this.
Right. They even have it like going even more negative when it repolarizes. So you have a hyperpolarization, but it's not clearly indicated there, but that's something that they will expect you to know about. So they could ask a question on that. That's a really good piece of insight of like, listen, like if it's something that they expect you to have some knowledge of, that means they're more likely to ask some questions on that.
Yeah. So wrapping up this passage, a nerve conduction velocity test, NCV, exploits the electrical properties of neurons to test for nerve damage. We talked about this before on the podcast. In this test, 2 electrodes are placed on a patient's body with an electrical shock placed on one and the nerve response measured on the other. The pulse travels at a constant speed of 100 meters per second. Now, that first part of the paragraph, not super helpful, not super testable, right? Are they going to ask us a question about where do we place the electrodes? No, that would not be a good use of the questions, the limited number of questions that they can ask us. But that last sentence, we've seen time, we've seen distance, and now we're getting a speed. That should be an indication that we can get a question related to any of those numerical values we're given. And so when I see these numerical values on test day that are built into the actual passage itself and are relevant to a potential question, I should have them in the back of my mind, and we should have them in the back of our minds when we go to the questions, because that's fair game, right? And we've provided a lot of potential questions, and obviously there are only 5 questions for this passage, so not necessarily all of them will be asked. But this comes back to this idea of going through the sample test as an opportunity to identify how to study, how to make those connections, and also how the AAMC test writers think, right? Because if you can, as you're studying, learn to predict questions, you're going to make your actual studying, right, for the content more efficient and more effective.
Yeah. You'd be surprised once you get really good at predicting, like finishing a passage, there's actually it's very rare that you get big curveballs. Like, oh, I didn't foresee that they could ask that. Like the MCAT, like there's only so many questions they can ask in the context of the stuff that they're testing. They definitely have like a style that as you see enough stuff, you're like, okay, this is what they're doing here. I see it. And that makes it so much easier on your actual test day. So we have our first question here. After finishing the passage, we're going to take a look at the questions. This is a very interesting question because it's actually kind of a graphical thing, but it really depends on your understanding of electric fields. This is, I feel like, one of the perfect questions to like illustrate how the AAMC wants to test you. Is like to answer this question, you have to understand neuro, you have to understand membranes, you have to understand electric fields, and all of those have to come together to answer just this one question. So the question itself, which image best illustrates the electric field lines between the inside of an axon and the surrounding extracellular solution? And so as we look at this, we have the electric field lines just going out of the membrane, going into the membrane, going towards the axon anterior, or going away from the axon anterior. I'm guessing axon anterior, like they don't really even, like that's just the interior of the axon. There's no context here for like which side is the cell body on and which side is the synapse on. And so, I mean, just off of that, C and D, there's literally no way to tell the difference between those two because they don't tell you which direction action potentials are going. And so, like, that makes life a lot easier. Like, C and D just don't make any sense in this context. But looking at what's going on with the other two, right? This question depends on your understanding of what's happening in a neuron. So in a neuron, you're going to be pumping 3 sodium out and 2 potassium in your neuron. And so as you pump this over time, there's a really good mnemonic that I like that's Nokia 321. Nokia 321. That's just telling you that sodium, Na, is out, and you pump 3 of them. Potassium is in, and then you spend 1 ATP to get that done. So it's sodium out, potassium in, ATP 3 to 2 to 1 is the ratio of those. Really like quick mnemonics if they're good, and that's one of my favorites. But overall, we can see that if we're pumping out 3 positive charges and we're pumping in 2 positive charges, overall, the outside is going to get more positive and the inside's going to get more negative comparatively. And so as a result, we're going to create an electric field. Now, electric field lines always point from positive to negative. So they're always going to be going in this direction. And so that means B has to be my answer. Note that if they asked when it was depolarized, that would be different because these graphs are always showing the charge inside compared to outside, -60 versus +60. So that can change.
This is part of why I love that we're doing this. We think about these questions differently. So if we think about how we can use the passage to our advantage, if we are concerned and we're blanking out, we know that the potential difference across the membrane is negative. And we know then that the inside is going to be relatively negative. So like you said, with the electric field lines, they're always going to go in the direction that a positive test charge would move in. So hence the positive to the negative. If the inside is negative relative to the outside, the arrows have to point in. That's it. And it also tells you, right, that you want to think about how it's going to move these potential positive test charges. They wouldn't go parallel to the they wouldn't go perpendicular to the difference, right? They're going to go parallel to the actual difference itself. So that's another way that when I look at C and D, I'm like, doesn't make sense. There's no difference within the axon itself that we're told about. We're told about the difference between the inside of the axon and the outside of the axon. And so I can, even when I'm panicking on test day, let's say that I'm like, oh my gosh, this is Chem Phys. Why do I have to remember the sodiums and potassiums? You can still use the passage in a sense, against itself. And so you can use the information that you're given, which they didn't have to give you. This is something that you should know, that the inside of an axon and a neuron is negative relative to the outside. You can use that to your advantage here with the questions as well.
Yeah, absolutely. Overall, not too tricky of a question. It's not a lot of calculation stuff, but you do still need to understand electric fields and neurons to be able to answer it.
And it's a really conceptual question, which the AAMC also likes doing. And likes asking. So have that in the back of your mind when you're approaching questions. Hey, I can get something that's actually really conceptual, and use that to your advantage as well.
Yeah, I think that's unlike, I feel like that doesn't happen in undergrad. Like if I'm going to get questions on electrostatics, they're going to be calculation questions on my physics exams. Mm-hmm. But the AAMC understands you only have so much time to answer questions, and they're more interested in seeing, do you really understand this? And so they like to throw curveballs by mixing electrostatics in with neuro, and that sort of thing allows them to test, do you understand this really well conceptually, which is what they're more interested in overall. The calculations that they tend to give you tend to be actually quite simple calculations, but it's hard to figure out how do I supposed to deal with this, because they like to test it in weird ways.
Yep. All about relationships. So, question number 6. One function of the myelin sheath is to. So right off the bat, this is a pseudo-discrete, right? I should know what the myelin sheath does. This is not something that they explicitly told me in the passage. Mm-hmm. So looking at the answer choices, insulate the axon from the surroundings. Sounds about right. Decrease the radius of the axon. Well, actually, even from our brief look at the passage and the table, we know that it doesn't affect it at all, right? Yeah. And so even if we're not sure on test A, we can definitely get rid of B. Then producing the Schwann cells. This is opposite. The Schwann cells make up the myelin sheath, right? They're just wrapped around the axon. So students that are just looking for familiar words, they're going to be tempted because they're like, oh, Schwann cells, I know this, and click and move on. But this is why, similar to CARS in the sciences, you really need to read each answer choice and identify what exactly is it saying, right? Because familiarity is not enough to get you through this exam. It's just not. And then increasing the capacitance of the axon. So again, even if I am unsure, when we look at that table, it's actually the opposite, right? So when it's myelinated, if you look, we said that the larger the negative exponent, the smaller it is. And so in the myelinated case, it's to the -10th, and in the non-myelinated -7th. So D's opposite leaves us with A.
Yeah, I feel like D is one of those answers that could be really tempting if they didn't give the table. But once you go back to the table, it's no, that's clearly wrong here. I do want to touch on your Schwann cell thing. That happens all the time where students are yeah, myelin and Schwann cells, those go together, and they just want to pick it. But no, Schwann cells make myelin, specifically only even in the peripheral nervous system, which is something I think you should know, versus oligodendrocytes in the central nervous system make myelin. But just because something is familiar, the MCAT likes to just slightly twist stuff in here. And so B, C, and D, none of those make sense. A does.
It's a combination of, are you paying attention and do you really know the concepts?
Yeah. I will say, like you pointed out, this is a pseudo-discrete. Technically, you should be able to answer this question without even reading the passage. And that happens a fair amount of time.
And also, I don't think I don't know if we've defined pseudo-discrete, even in the last one, but when we say pseudo-discrete, you have the discrete questions, which are not associated with a passage. When we say pseudo-discrete, it means it's technically within a passage, but you don't actually need the passage to answer it.
Yeah. It's essentially a discrete question that has somehow gotten tied to a passage itself.
Yeah. It's the topic relationship. That's it.
Yeah. Yeah. So we have the next one, which is channel X transmits only the smallest substances dissolved in the extracellular fluid through the axon membrane. Which substance does this transmit? This is another pseudo-discrete, the actual passage information. There's nothing in here about channel X in the passage. Everything is contained in the question itself. Now, you may need the periodic table to answer this, but as we look at this, basically they give you the context of, we just need to find the smallest thing, right? That's what they're going for here. And so which of these is going to be the smallest? Now, I think A is one you should immediately be able to cross out. because a protein is made of lots of atoms, right? Like there's carbons and oxygens and nitrogens and hydrogens in every single like amino acid. And then proteins are made up of lots of amino acids. And so this is going to be way bigger than any just one atom. Now, between the other ones, we have sodium, potassium, and chloride. Pull up the periodic table. Chloride is number 17, potassium is 19, and sodium is number 11. The ions, like sodium is going to be the smallest of these. Sodium ions lose an electron, and so they're about the size of neon. Chloride ions gain an electron, so they're about the size of argon, and potassium gains an electron, so it's also about the size of argon. So potassium and chloride are going to be about the same size. There is some difference in there that I would go through in another question, but like this one's just like really clear. It's sodium. Sodium's the smallest. Just pick that and move on. Should be able to make it through that question relatively quickly.
And so many students are going to see channel X. They're going to try and go back to the passage. It's not necessary. You know, you didn't see channel X. It's not in there. And when, like you were saying, you see that the question stem tells you exactly what it's looking for, that's it. You don't go back. You do not worry. And you just look for smallest. And a lot of students forget that the periodic table exists on the MCAT interface. Use it. You do not need to memorize every single atom on the periodic table. It's not worth your time. So use it. You should be familiar with the periodic table, how to use it, the general trends. But on test day, that's what it's there for.
Yeah, exactly. I do want to say, I just kind of want to point out, there's a lot of people who are going to look at this passage and immediately freak out because it's circuits and they feel not confident in circuits. But I just want to point out, we've done 3 questions and 2 of them just don't require the passage at all. And that's a pretty common thing that happens on the exam, is that even if the passage is really difficult, there's going to be some questions that even if you didn't read the passage, you could get correct answers for. Note that that is different for cars. I want to point that out. Like, I do think on test day, if you are really scrambling for time, which is not where you want to be, and like hopefully never happens to anyone, but if that happens and you're in the science section, try to answer some questions without reading the passage, because there are some passages where you can answer half the questions correctly without actually reading anything. Don't try that in cars. Does not work in cars. But It's one of those things that just works in the science sections.
And this is why I think, we need to be wary of like triaging the difficulty of passages. And the idea being, some people will tell you, okay, like look for the passage that looks easiest. And we just saw that this passage looks really intimidating. Questions are not at all. And so This is why you want to get comfortable going through and not jumping around the entire exam.
Yeah, exactly. So let's go ahead and look at the next question here.
So question number 8, what is the closest distance the electrodes used in an NCV test can be placed on a nerve in order to measure the voltage change as a response to the stimulus? So we want distance. And guess what? We were given the information that we need for this in the passage, specifically at the end. So if we want distance, we need 2 other variables. We need time and we need velocity, right? We're given the speed, which is just in the same direction of 100 meters per second. Now, if we want the closest distance they can be placed, we want what's the smallest unit of time that I can measure. And so we're given that in figure 2. And because we took a brief look at figure 2 before we got to the questions, we know where it is. We don't have to go digging in the passage. And so all we're going to do is we're going to multiply the speed by the time, and that gives us the distance. And so if we have 100 meters per second and we have 1 millisecond, that's 1 times 10 to the negative 3. And so what I like to do is I like to just draw the little arrows to move the decimal point. So we're going to move it over 3 spaces, and that would give us 0.1 meters, which is B.
Yeah. So we have 1 millisecond. That's just, I know this is, as you mentioned, 10 to the minus third.
It's good to see it.
Seconds, right? And if you just take that times 100 meters per second, 100 meters per second, note that the seconds cancel out and you're left with meters. And so 100 times 1 or times 10 to the minus third, that's just going to be 10 to the minus 1. So that's going to be 0.1 meters at the end of that. I do want to point out, a lot of times, a lot of the challenge for students is knowing where to go to find the answer. There's a lot of students that might try to get sucked in by like what's going on here. I'm betting that there's a fair amount of students that pick C just because 1 meter is mentioned in the passage, right? But there's also, looking at this, like they're asking us what's the distance of the electrodes themselves, not the distance of the neuron, right? So like how close can we place these electrodes in the neuron? But they also straight up just mention the NCV test. So for me, like I read that, I'm like, oh, where do they talk about that test? It's the very last bit. And so that tells me, okay, this is the only time they talk about the NCV. So my answer choice has got to use this thing in here. And that makes things a lot easier.
The other cool thing is, and again, this is going to be based on how engaged you are in the passage and the questions. At the beginning, when we're told the 1 meter, that's the longest, right? Mm-hmm. In the question stem, we're asked about the closest distance. And so that right off the bat should be a hint that, hey, 1 should not be, or 1 will probably not be the correct answer, right? Because then you'd have to go across the longest neuron. Wouldn't make a whole lot of sense for all of the smaller neurons, all of the smaller axons when we're trying to figure out if there's damage.
Yeah. I just want to point out D also makes no sense. If the longest neuron is 1 meter, like what's the closest you can place these electrodes on this neuron? 10 meters? That like there's no neurons that long. Like we can't do that unless you're a squid. Like you don't have 10-meter long neurons.
Exactly. Where are we going to get 30 feet?
That makes no sense. Exactly. So looking at our last question here, I think this is our last question. Yeah. Mm-hmm. So what information about an axon is required to calculate the current associated with an NCV pulse? Now, as we look at this, a lot of students are going to be like, oh, like the NCV thing, go back to this. But this isn't a calculation. There's not a lot of information here for this. This is absolutely going to be another one of those pseudo-discrete questions, right?
And it's also conceptual, right?
Yeah.
All of our answer choices are words, not numbers. And so we're looking for the relationships.
Yeah. And I think paying attention to units is also really key in the sciences. But they're asking you to, like, how do we calculate the current? The very first thing that should probably come to your mind is Ohm's law, which is just V equals IR. And so this is one of our bread and butter circuits equations. I would say this is the bread and butter circuits equations. I've never seen the MCAT test a calculation question with circuits without using this at some point. They might also use some other equations, but like this is one of the main go-to ones. And so we just want to figure out, like, what do we need in order to calculate current? In order to calculate current, we need voltage and we need resistance. The problem is, as I look at the answer choices, that's not an option, right? There's nothing that says voltage and resistance. I do want to kind of point out, this is where like the MCAT like turns up the difficulty by using some slightly different language than they know you're comfortable with. Still correct, but they like to say like radiation instead of photon, right? Or light. They like to say potential versus voltage. I think voltage tends to be more comfortable in students' minds, but electric potential is the exact same thing. So all of these that say potential, all of those are actually saying voltage. Now, if we just go through each one of these, right? Conductivity, resistivity, and length, that doesn't give me any of these things, right? Like there's nothing for me to do with that. So if we look at B, potential, that gives me the voltage. We also have conductivity and radius. There's no equation that the MCAT expects us to know about the conductivity, or to be able to find the resistance based on the conductivity and the radius without some additional stuff, right? Technically, somebody could calculate the resistance given the conductivity and the radius, but you would also need like the length of the neuron, because the longer the neuron, the more resistance there's going to be. There's a lot of different things kind of going on there, but for this, like, there's not really something we can do with that. I think C is closer, because there is an equation that the MCAT will expect you to know, that the resistance of a wire is equal to its resistivity times its length over its cross-sectional area. So like if we have the resistivity here and we have the radius, we could find the cross-sectional area, but we're still missing the length. And so we can't actually calculate resistance based off of this. It's almost there. Like if it said and length for C, all of a sudden, that could in theory work. But the correct answer here is actually going to be D. So we have the potential, which gives us the voltage, the resistance per length, and the length, right? Like if somebody said the resistance per length was 3 ohms per meter, right? If that was the resistance per length, and they also told me the length was like 2 meters, right? I could just multiply those two and the meters will cancel and I have the resistance. So that would be 6 ohms. And so giving me the resistance per length and the length, I can multiply those to find the total resistance. And so D is the only one that gives us both the voltage and the resistance in order to calculate that.
Yeah, and I love that, right? Like the units are so important in the sciences. And so what I always tell students is when you're making equation sheets, right? A place where you're going to have all of your equations consolidated, have the units, because you should be able to know what equations you need based off of the units, right? Now, I want to say something else that is very intimately tied with what you were talking about, using the resistivity to calculate the resistance. If I just see radius, that's perpendicular to the movement of the electrons, right, of the current. If I just have the radius, I don't actually know what's going on in terms of the movement of the current itself, right? So when I see just radius, I'm like, that doesn't make sense. It's the wrong direction if that's all I'm given, right? And so again, notice that for some of these questions, even just knowing the direction that things are moving can be helpful to get rid of wild answer choices. Right. And this comes back to the idea that the AAMC loves testing relationships and concepts. And so you want to make sure that you have those underlying concepts well understood before you start tackling a bunch of questions. And this is why brute forcing your way through a bajillion questions is not enough for the MCAT for most people, right? You want to make sure that you take the time, understand the content, the concepts, and then are able to actually apply them.
Yeah, I do. There's so much to like, I'm really trying not to spin off too much into teaching as we're going through this, because there's a lot of other relationships in here. And like, I'm just trying to hit the key important ones. I do think that on test day, it might be useful for students to know like conductivity and resistivity are just inverses of each other. So like if the resistivity was 5, then the conductivity is 1/5. Like they're literally just flipped of each other. And that's something that you would want to know for testing. And that's something we like go over in the course. But I do kind of want to take a moment and just let's just go through these questions and talk about how do we need to talk about and think about each one of these individually. We do have one other. Do you have anything else to say about this passage? I think this is a passage that overwhelms a lot of students when they first look at it, but really the questions are not that bad. Like there's a bunch of other passages in here that I think are actually have trickier questions, but I know at first glance, this passage scares more students than some of those other actually harder passages with more difficult questions.
I completely agree.
Yeah. So without, so kind of like stepping back from that, we also have another announcement, which is kind of an interesting thing. This is a new development. Some of you guys may be familiar with the Student Doctor Network. Student Doctor Network is a huge network that lots and lots of students use. Pretty much everyone who becomes a physician at one point is in there. So like, it's filled with a lot of pre-med students, a lot of medical students, even some physicians are in there pretty commonly. And it's a really good resource for students. We are now officially working with the Student Doctor Network. That's a big deal. As somebody who's been in the MCAT industry for a decade, they have not partnered with any prep company ever, period. The reason they're partnering with us is because we offer so many like valuable free resources. And I think it just speaks a lot that the Student Doctor Network, who has this really strong. We don't want to partner with anyone because we put students first. The fact that they are partnering with us just kind of goes to show. And I love seeing two organizations come together. Like, okay, we're putting students first. Like, what do students need? That's the most important thing. What's best for medicine? What's best for humanity? And so as a result, I'm really excited to announce that we are working with the Student Doctor Network. I know we're going to be doing some sessions with the Student Doctor Network specifically, as well as some other interesting things as a part of this partnership.
Yeah, go check out their Instagram if you haven't already. We also have an Instagram. Take a look at that, and they have some other resources as well. So we encourage you to take a look. And we're really excited about this partnership and putting you guys first.
Yeah, they have a pre-med planner app, which I think is particularly useful, a way to help students, organize all of their information for their actual application via AMCAS. I know you can find that. It's called the pre-med planner app, and then you can find it on like the Apple and Google app stores. So that's definitely something to be on the lookout for. I do find it very useful for students, and I'm really excited to be working with them, considering like I was using the Student Doctor Network for like over a decade before we kind of like have got to this point where we're partnered with them. And so I'm pretty excited to announce that partnership.